Welcome to qnawire.
Here, we have to find the centripetal force acting on a hammer that is released from its horizontal circular motion right after that initial point of release. So we know that the equation for our centripetal force equals mv squared over r. Now, we're given the radius of the circle in this problem, but we don't know our velocity. So we're going to have to solve for that before we do anything else. All right, so we know from the kinematic equations that the equation for x, the horizontal distance traveled by our hammer, is v0 t plus 1/2 times our horizontal acceleration times t squared. But this second term is going to cancel out because we don't have an acceleration in the horizontal direction. All of our acceleration comes from gravity, which is pointing straight downward. So x is just equal to v0t. All right, well, we don't know how long our hammer is going to be in the air, so how do we find t? To do that, we're going to look at the y component of our motion, which I've drawn on the right side of the screen here. Now, we know from another kinematic equation that our y velocity is equal to our initial y velocity plus a times r vertical acceleration times t. Now, there's a fact about projectile motion that is going to come in handy here. After a time t, so right before the hammer hits the ground, our velocity is going to be equal to the negative of our initial velocity. And that's because projectile motion is always symmetric, right? It forms a curve like this. So our initial velocity here is just going to be equal to the negative of our, or it's going to be equal to the velocity here, but negative. So that means that we can rewrite the equation that we just had, this one right here, and rearrange to solve for t, and we get that t is equal to negative 2v0y over a y. And I'll rewrite this so that it's a little bit more clear that y is the subscript here, not an extra variable. All right, and now, as you can see from splitting up the velocities, we can see that our y component is just is our actual velocity, v0, times the sine of theta. So this is going to be our final equation for t. So now that we have t, we can plug in to that first equation that we had for x. X is v0 times t. And we're going to get that x equals v0 and cos theta. So that's because we were initially working with v0x, which is just equal to this, which, like when we were solving for the initial y velocity, we can see from splitting up our velocity into components. So we get v0 cos theta multiplied by the value that we just found for t, sine theta over a y. And not necessary, but you can make the problem a little bit more simple by using a trig identity, which is that 2 sine theta cos theta is equal to sine of 2 theta. Now we're going to use that identity, and we're going to rearrange the equation above to solve for v0. And we're going to get that it's equal to negative x times ay over the sine of 2 theta. Now we're going to plug in our givens, and those are going to give us negative 81.75 meters, how far it travels, times our vertical acceleration, which is just gravity, so 9.8 meters per second squared, all over sine of 2 times 41, which is the theta that we're given in the problem. When we plug all of that into a calculator and solve, we find that v naught is equal to 29.3 meters per second. And so the last step is to plug into our equation for Fc, mv squared over r, And we know the M of our hammer, it's 7.3 kilograms, multiplied by our velocity that we just found, squared, and dividing by our radius, 1.8 meters. And we find that that is equal to 3,500. Our units are kilograms meters per second squared, which makes sense since those are newtons, the units of force. So we know that our answer makes sense, and that is our final result.